We know that we can use span to turn a collection of vectors into the smallest subspace of the ambient vector space containing those vectors. But one unfortunate feature of span is that it doesn't always make it clear exactly what the subspace that you're getting actually is, or if you have two different collections of vectors, say these two collections, it actually, using span to generate a subspace containing each of these collections of vectors doesn't really make it clear if you're getting the same subspace or different subspaces. So let's take the opportunity to just see how we could check if these two spans are actually the same subspace or different. I guess the first thing we need to do is actually write down what each of these sets is, right? To check if these two sets are equal, we're going to have to sort of dig into their definitions. So this first one, this is the collection of all vectors that look like a1 times the first vector plus a2 times the second vector, 0, 1, 0, where a1 and a2 are just real coefficients, right? So every combination of real coefficients gives you a vector in this span. Now for the second collection, we get something that looks very much the same, except the vectors we're using are different. I'm going to use different variable names for the coefficients. You'll see why in a minute. So the second span is the collection of vectors that look like b1 times 1, 1, 0 plus b2 times 1 minus 1, 0. And again, b1 and b2 are in the real numbers. Okay, so how could we check if these two are different or equal? Since they're both sets, so let me call this one S1 and this one S2 for span 1 and span 2. So a nice way to check if two sets are equal is two sets are equal exactly when the first one is contained in the second one, and the second one is contained in the first one, right? So what we can do is to check if these are the same, just see if this first one contains the second, and then check if the second contains the first. All right. So first let's check that. So one of these is harder than the other. Let's check that S2 is contained in S1. All right, so I'm going to show that this span is contained in this span. Well, first of all, 1, 1, 0 it's 1 times 1, 0, 0 plus 1 times 0, 1, 0, right? So what we've done here is we've expressed 1, 1, 0 as a linear combination of these two, but these are the two vectors that we're taking the span of. So what this shows is that 1, 1, 0 is in the span of 1, 1, 0, 1, 0, 0 and 0, 1, 0. Okay, similarly, right, we can use a similar trick. I'll let you fill in the details. I guess not an exact quote. I'll let you fill in the details, but we can show that 1 minus 1, 0 is also in S1, right, the span of 1, 0, 0 and 0, 1, 0. Well, if both of these vectors are in this span, then the span of these two vectors also has to be in this span, right? Because S2 is the smallest vector space that contains 1, 1, 0, the smallest subspace that contains 1, 1, 0 and 1 minus 1, 0. Well, if S1 also contains these two and is a subspace, then it must contain the smallest subspace. So that means that S2 contains S1. Okay, well now we need to check the other containment. So now let's check that S1 is contained in S2. All right, so how can we do this? Well, again, because the span of a collection of vectors is the smallest subspace that contains those vectors, we just need to check that our spanning vectors 1, 0, 0 and 0, 1, 0 are both in S2, right? If each of these is in S2, then the span of these two is also contained in S2. So how can we check if these two are in S2? Well, we have seen how to do that. We just need to figure out if we can express each of these vectors as a linear combination of the spanning set for S2. So the spanning set for S2, so what we need to do is solve this equation. We want to know, can we write 1, 0, 0 as a linear combination? So some vector A times 1, 1, 0, some scalar A times 1, 1, 0 plus some other scalar A times 1, minus 1, 0. Okay. Well, so how would we answer this question? Well, what we're going to do is solve, right, this is really a linear system with 3 equations and 2 unknowns. So we can solve this by doing row reduction on an augmented matrix, and the augmented matrix is going to be, right, this is the left-hand, this is the constant side of the system, right? And the side containing all the variables is going to be 1, 1, 0, 1, minus 1, 0, right? Now we're going to need to do the same thing for the other vector 0, 1, 0, right? That's going to be, so we also need to solve this. I'm going to use, well, okay. I'll use different variable names. We'll see in a second that it's really not going to matter what we call these variables. So we need to know, can we express 0, 1, 0 as a linear combination of these two spanning vectors? To do that, we would solve the linear system represented by this augmented matrix. 1, 1, 0, 1, minus 1, 1, 0, 0, 0. All right, and here's our augmented matrix. Okay. Well, to do this, we're going to row reduce both of these matrices, but remember, when you do row reduction, what part of the matrix determines, when you're row reducing an augmented matrix, what part of the matrix determines what row operations you do? It's just this part, right? But this part is the same for both of these matrices. So if we row reduce to these separately, we would actually be doing the same row operations for both of them. So there's no reason to do one and then the other. We can actually do both at the same time. All we need to do is, so right here's the unaugmented part. So when we do row reduction, we just need to keep track of what happens to both augmented columns. So here's one augmented column and here's the other. Right? So we can solve both of these systems at once just by row reducing this matrix. So what are we going to get? So let's see. I guess we need to do R2 minus R1. So that's going to give us 1, 1, 1, 0, and then 0, minus 2, minus 1, 1. And then 0, 0, 0, 0, of course. And now we can do R2 times minus a half. So that's going to give us 1, 1, 1, 0, 0, 1, 1 half, minus a half, and then of course 0, 0, 0, 0, and 1. So now I need to do row 1 minus row 2. I get 1, 0, 1 half, 1 half, 0, 1, 1 half, minus 1 half, 0, 0, 0, 0. Okay, so remember we have two augmented columns here. So on the one hand, this is telling us A1 has to be a half and A2 has to be a half. That's coming from this. And then also B1 has to be a half and B2 has to be minus a half. And that's coming from this. All right. So what we've done here is we've shown that 101 is 1 half times 110. Sorry, 100 is 1 half times 110 plus minus a half. No, plus a half times 1 minus 10, and 0, 10 is 1 half 110 minus 1 half times 1 minus 10. All right, so we've displayed each of these vectors as linear combinations of these vectors. So that means that 1, 0, 0 and 0, 1, 0 are both in our second span, and that means that the entire first span is in the second span. All right. So what we see here, so the upshot of all of this is that these two spans, even though they're the spans of different vectors, as subspaces, these two spans are actually the same subspace. They contain the same vectors. So that's one tricky thing about span. It can be hard to tell whether you have genuinely different vector spaces or not. And we will see that that will have some impacts on on the types of vectors we choose to write down spans.